Now we are going to discuss second law of application. Second application, that is electric field due to uniformly charged sheet. Last class we were completed first law of Gauss application. Next, second law Gauss application is electric field due to a uniformly charged sheet. For that, consider an uniformly charged sheet. This is one uniformly charged sheet, infinite sheet. Charges are placed on this uniformly charged sheet. It is a uniformly charged sheet. Now, at this point, we have to find out electric field intensity due to this charged sheet. Due to this charged sheet, at this point we need to find out electric field intensity. If we want to apply the Gauss law, compulsory we need a closed surface. So, which type of closed surface we can assume here? Here we can assume cylindrical Gaussian surface passing through the sheet. Charges are placed both sides. Here charges are there and back side of the sheet. For example, this is sheet. Here charges are there, here charges are there. Clear? Now, consider a Gaussian surface. This is Gaussian surface, cylindrical Gaussian surface passing through the sheet. Now, how many closed surfaces we can see here? This is one closed surface, this is one closed surface, and this is one closed surface, this one, and this is one closed surface. This surface area vector is this direction, take it as ds1. This surface area is ds2. Here, due to this one, electric field direction is this direction, and here this direction, electric field direction. And this closed surface area is vector surface area is this direction. This one is this direction. 4 closed surface areas are there. Now, between this surface and electric field is 0 degrees, and this surface and electric field is 90 degrees, and this surface vector area and electric field is 90 degrees, and this one is 0 degrees. Already we know flux passing through a closed surface. What is the formula? Circle integral EDS is equals to Q by epsilon naught. This is the flux passing through a closed surface formula, Gauss law. This already we can write as EDS cos theta is equals to Q by epsilon naught. Here theta is the angle between electric field vector and surface area vector. For this surface 90 degrees, for this surface 0 degrees, this one 0, and this one 90 degrees. So, flux passing through this area is 0 because of 90 degrees. Flux passing through this area is also 0 because of 90 degrees, and flux is existing through this surface and through this surface because of angle is 0 degrees. By solving this one, flux is through ds3 and ds4 is 0. This one because of theta equals to 90 degrees. Now, flux passing to this one is existed. Total flux passing through Gaussian surface we can write as total flux passing through Gaussian surface is this one and this one. What we can write? This one, circle integral E dot S1 plus line integral E dot ds2 is equals to q by epsilon naught. Here ds1 theta is 0 degrees, ds2 which is equals to q by epsilon naught. Now total surface area I am taking as S, and this is also taking as S. ES is equals to q by epsilon naught. 2 ES is equals to q by epsilon naught. Now E equals to q by 2 epsilon naught into S. Here q by S is the surface charge density. Q by S is the surface charge density. Then how to write final equation? We can write as final equation E equals to, this is we got into S, this is we can write as 1 by 2 epsilon naught into q by S. Here charge by surface is nothing but a surface charge density, that is sigma. So E is equals to sigma by 2 epsilon naught. This is the electric field intensity due to uniformly charged sheet. Here sigma is surface charge density. E is equal to sigma by 2 epsilon naught. Here sigma is the surface charge density. Surface charge definition is what? Charge existing per surface is called unit. Charge existing per surface is called surface charge density. Sigma is equals to q by epsilon naught. This is the second application of Gauss law. Electric field due to two charged parallel sheets. Consider two parallel sheets. This is one parallel sheet and this is one sheet. These two are parallel to each other. And this one charges are there. Now at this point we need to find out electric field. At this point we need to find out electric field. At this point we need to find out electric field. These two are the parallel charged sheets. What is the electric field is existed? Point 1, point 2, point 3. 3 points we need to find out electric field intensity. First at point 1, first we discuss this one. At point 1, due to this one electric field is going to be existed, due to this sheet is also electric field is going to be existed. Just before only we discussed electric field intensity at a point due to a charged sheet. We have the formula, that formula we can apply here. Now at point 1, this sheet is going to be existing one electric field, this sheet exists one electric field. Due to that two sheets, one electric field is going to be existed. This is sheet A, this is sheet B. Surface charge density on this sheet is sigma A, surface charge density on this sheet is sigma B. Now at point 1, electric field region due to A sheet and B sheet. Due to A sheet, due to this one, what is the formula? Sigma A by 2 epsilon naught minus. Why minus? Because of left side of the sheet. Next, for this one, due to B sheet is also minus, because of it is also left side only. Now, what is the total electric field intensity? 2 epsilon naught minus sigma A plus sigma B. This is the electric field intensity due to this sheet and due to this sheet at point 1 in the region 1. Next, at point 2 we discuss here. This point is right side of this sheet, left side of this sheet. So, what we can write? E is equals to right side of A sheet. So, it become as sigma A by 2 epsilon naught. For this one, left side. So, sigma B by 2 epsilon naught. E net can be written as 2 epsilon naught sigma A minus sigma B. Clear? Next, at point 3, this point, this is right side of B sheet and as well as right side of A sheet. So, E can be written as sigma by 2 epsilon naught, that is sigma A, plus sigma B by 2 epsilon naught. Now, E is equals to 2 epsilon naught sigma A plus sigma B. This point is, observe here at point 1 electric field E is equals to minus of sigma A plus sigma B by 2 epsilon naught, because of this point is left side of A sheet and left side of B sheet. Next, take it at region 2, point 2. Point 2 is right side of A, so that is why it is plus. Point 2 is left side of A, that is left side of B, that is minus. So, E is equal to sigma A minus sigma B by 2 epsilon naught. For point 3, right side of A sheet only and right side of B sheet only. So, here sigma A plus sigma B by 2 epsilon naught. So, this is electric field due to two charged parallel sheets. Now, we discuss one more application due to conducting sheet. Electric field at a point due to conducting sheet. Electric field at a point due to conducting sheet. What is conducting sheet? For example, I am taking one sheet. If charges is given to this sheet, total charges are accumulated on the surface. Surface charge density, take it as sigma only, sigma only. Now, consider 3 points P1, P2, P3. Now, we discuss electric field at point P. At point P1 we discuss E is equals to here sigma by 2 epsilon naught plus sigma by 2 epsilon naught only. Due to this one sigma by 2 epsilon naught, due to this one also sigma by 2 epsilon naught, then E is equals to 2 sigma by 2 epsilon naught, 2 cancel, then sigma by epsilon naught. It is not at 2 sheets, it is only single sheet. So, due to this one, even left side also it is a conducting sheet, that is why here we are taking as sigma by 2 epsilon naught plus only and sigma by 2 epsilon naught. Next, at point P2, at point P2 we have to discuss, point P2 is for this charges it is a right side, For this charges, it is a left side. So, E is equals to sigma by 2 epsilon naught due to this charges. Due to this side charges, it is 2 epsilon naught. Then we get as 0 because of point P2 is existing on the sheet. Due to this side is positive, due to this side charges is negative. That is why E net will become as 0 at point P2. And coming to at point P3, point P3 is right side of this one and right side of this one also. So, E is equals to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. Then E is equals to 2 sigma by 2 epsilon naught, 2 cancel, then sigma by epsilon naught. So, what we observe, for a conducting sheet, the point is existing either left side or right side, E net is equal. The point is existing on the sheet, then E will become as 0. Clear? Now, basing on this, we will discuss some problems. Two parallel plane sheets 1 and 2 carry uniform charge. An example problem. Two parallel sheets 1 and 2, uniform charge density is sigma 1 and sigma 2 as shown in figure. Clear? What is that? Here they are giving figure. This is one sheet and this is one sheet. This sheet having the charges and this sheet having the charges. This is sigma 1, this is sigma 2. Here they are taking the regions 1, 2, 3. This is second region, this is third region. This is one sheet, this is one sheet, and this is one region, this is second region, this is third region. Then what they are asking, the electric field in the region marked 1 is. So, they are giving as sigma 1 greater than sigma 2 condition. Clear? This is the diagram they are giving. This is the diagram. Two parallel sheets 1 and 2, this is one, this is second sheet, carry uniform charge density sigma 1, sigma 2 as shown in the figure. The electric field in the region marked 1. At this point they are asking electric field region. This already we discussed, sigma 1 greater than sigma 2, surface charge density of this one is greater than this one. Now, for this sheet, this is sheet 1, this is sheet 2. For this one, this point is left side only, and this point is for this case left side only. Now, in region 1 at this point is left side of that one. Already we know E net is equals to minus of sigma A plus sigma B by 2 epsilon naught. Just we discussed, just before only we discussed. So, apply this formula for that one. E net is equals to minus of sigma A is nothing but a surface charge density is the first one, plus sigma B is nothing but a surface charge density of second one by 2 epsilon naught. This is the net electric field in the region 1. Due to this one, sigma 1 by 2 epsilon naught minus, due to this one also sigma by 2 epsilon naught minus only. but this one electric at point 1 due to this one negative only, at point 1 due to this also negative only. So, final answer is minus of sigma 1 plus sigma 2 by 2 epsilon naught. Third application, electric field intensity at a point due to charged spherical shell, due to a charged spherical shell. In that three cases are there. Case 1, point is outside the shell, point is outside the shell. See here, this is uniformly charged shell, electric field intensity at a point due to a charged spherical shell. Charges are accumulated or placed on the surface. The radius of this sphere I am taking as capital R. Clear? Now, at this point, what is that case 1? Point is outside the spherical shell. Now, this is at this point, how much distance from the center? Small r distance. At this point, we need to find out electric field intensity. Clear? If you want to, for example, we want to apply the Gauss law, compulsory we need a closed surface. Am I right? Now, which type of closed surface we can assume here? See, is spherical Gaussian surface. This one is Gaussian surface. Now, consider a small part of region. This surface area direction is this direction. At this point, electric field is also this direction. Clear? Now, first flux passing through this surface. Flux passing through ds surface area. Flux passing through ds surface area we need to find out. So, apply the Gauss law, already we know EDS is equals to Q by epsilon naught E dot. So, ds cos theta, theta is 0. So, Q by epsilon naught, circle integral ds is equals to Q by epsilon naught. Clear? ds, integrating this part, integration of this part will give the total surface area of the Gaussian surface E into 4 pi r square by Q epsilon naught E equals to Q by 4 pi epsilon naught into r square. Here Q is what? Charge existing on the spherical shell of radius capital R. Now here surface area, surface charge density sigma is equals to, surface charge density sigma is equals to Q by SRA, which is equals to Q by area of this sphere is nothing but a 4 pi capital R square. Now substitute there. This value from here Q is equals to can be written as sigma into 4 pi r square. This value substitute here, then E equals to by 4 pi epsilon naught into r square. 4 pi cancel, E is equals to sigma r square by small r square. This is the electric field intensity at a point outside the spherical shell. Electric field intensity at a point due to a charged spherical shell we need to find out. In the three cases are there. First case is what? Point is outside the shell. Here point is P here. How much distance from the surface? Sorry, from the center of the spherical shell? Smaller distance. Now at point B we need to find out electric field intensity. What we got? E is equals to sigma by epsilon naught into capital R square by small r square. This is the electric field intensity due to this charged spherical shell at smaller distance from the center. Point is outside. Next, second case, point is on the sphere. The point is on the sphere. Case 2, point is on the sphere. Point is on the sphere. Second case. Now, this is sphere of radius capital R. Charges are placed on the sphere. Now, already we got point is outside, electric field intensity we got. Now, point is existing on the sphere. How much distance? Smaller. Now, at this point we need to find out electric field intensity. For that what we have to do? Construct a Gaussian surface. Gaussian surface and original sphere both having the same radius. So, in this case what we can write? Simple, what we can write? Small r is equals to capital R, that is it. Outside what we got? E out is equals to what we got? Sigma by epsilon naught into capital R square by small r square we got already. Here on the sphere means small r is equals to capital R, just to substitute there into capital R square by capital R square. So, sigma by epsilon naught, it is on the sphere, this is out the sphere. This already we know equation, we got just before only. E out is equals sigma by epsilon naught into capital R square by small r square. E on the sphere is sigma by epsilon naught. If the point is existing inside the sphere, then what is the electric field intensity? Third application. In this case 3, point is inside the sphere. Point is inside the sphere. Then what we will get? This is radius is capital R. Now, point is here. How much distance? Take it as small r. Construct a Gaussian surface. This is Gaussian surface. Clear? But charges is existing only on the sphere. Inside the shell, there is no charges. So, inside the shell, total charge Q is equals to 0. Inside the shell, there is no charges. Clear? Charges are existing on the sphere only. Q is the charge existing only on the sphere. Inside the shell, there is no charge. Q is equals to 0. Then how to write? E in is equals to Q is 0 means there is no surface charge density. That is E in is 0 because of sigma is equals to 0. There is no inside charges. Inside the shell Q is equals to 0, that is why E is going to be 0. Now, we observe the graph, the sphere electric field intensity. This is E and this is small r, distance. This is electric field intensity, this is the distance. Now, what we observed from center of the shell, this is center of the shell to surface, there is no electric field intensity. At the surface, it is maximum. After surface, so it is decreasing. E inversely proportional to R square. This is R is equals to R. Here electric field on the surface, sigma by epsilon naught. Here on the surface, maximum is going to be existed. From the surface we are moving out. If the distance is inversely proportional, electric field intensity is inversely proportional to the square of the distance. So, it is decreasing. This is the graph we observe in case of uniformly charged spherical shell. From origin, say this is center of the sphere to surface, there is no electric field intensity. On the surface is maximum. Moving away from the surface, electric field is going to be decreasing, we observe. Now, we discuss some problems. Conducting hollow spheres of radius R1 and R2 have charges Q1 and Q2 respectively. Have charges Q1 and Q2. Two concentric conducting hollow spheres of radius R1 and R2 have charges Q1 and Q2. If R1 greater than R2, R1 greater than R2, then the electric field intensity at a distance smaller from the common center, then the electric field intensity at smaller distance from the common center. Two concentric conducting hollow spheres of radius R1 and R2 have charges Q1 and Q2. If R1 greater than R2, then the electric field intensity at a smaller distance from the common center, that is, again case is given smaller R2. So, two concentric conducting hollow spheres radius R1 and R2 have charges Q1 and Q2. This is one sphere whose radius is R2. This is one sphere, this radius is R1. Now, this is given to Q1 charge, this is given to Q2 charge. This is given to Q2 charge. Now, where we have to find out electric field intensity? Where we have to find out electric field intensity? Smaller distance from the common center we need to find out. So, this one. At this point, how much distance this one? Smaller distance. Now, assume a Gaussian surface. Now, this point is outside of this spherical shell, inside of this spherical shell. Point P is the Gaussian surface. At this point, we need to find out electric field intensity. Two concentric conducting hollow spheres of radiuses R1 and R2. This is common center. Concentric means common center. Having charges Q1 and Q2. This is having Q1 charge, outer sphere radius is R1, inner sphere radius is R2, inner sphere having the Q2 charge. Now, then the electric field intensity at a smaller distance from the common center at this point. Condition is given R1 greater than smaller greater than R2. So, smaller is existing between R1 and R2. Clear? So, inside of R1, outside of R2. Now, this point is for this sphere outside, for this sphere inside. So, already we know inside of the sphere there is no charge affected. So, due to this one electric field is 0, and this is going to be existed one electric field that we need to find out. What is that? So, point R is inside of Q1 charged sphere and outside of Q2 charged sphere. Clear? Point R is inside of Q1 charged sphere. This is Q1 charged inside and outside of Q2 charged sphere. So, inside Q1 charged sphere, so there is no effect. Now, E net is equals to E electric field due to Q1 charged sphere, electric field due to Q2 charged sphere. This is going to be 0. This is 0 plus E Q2. Now, already we know the formula. A point is outside the charged spherical shell, we have the formula. So, apply for that. Now, E net is equals to, what is E Q2? 1 by 4 pi epsilon naught Q2 by R square. Just now only we got. This point is outside of this spherical shell. So, this spherical shell is going to be affected some amount of electric field intensity, that is E net is equals to 1 by 4 pi epsilon naught Q2 by R square. So, what is the answer? Answer E is equals to 1 by 4 pi epsilon naught Q2 by R square. This is the electric field intensity at this point. This point is inside the Q1 spherical shell, outside the Q2 spherical shell. We discuss one more problem. The electric field capital E is uniform and is parallel to the axis of hemisphere and it is parallel axis of hemisphere of radius capital R radius capital R. The flux passing through the hemisphere hemisphere is. The electric field capital E is uniform and it is parallel to the axis of hemisphere of radius capital R. The flux passing through hemisphere is. Hemisphere is hemisphere. What is its radius? Capital R. What they are giving? Electric field is uniform and is parallel to the axis of hemisphere. This is axis of hemisphere. This is electric field. Clear? Electric field is parallel to the axis of hemisphere. Now, flux passing through the hemisphere we need to find out. Flux formula already we know. What is that? Total flux pi is equals to line integral of EDS. Line integral of EDS. E dot ds. Pi is equals to line integral of EDS cos theta. Here theta is 0 degrees because of surface area and electric field is parallel to each other. Then pi is equals to ds. Here theta is equals to 0 degrees. Then this is going to be 1. Pi is equals to EDS. E into, if it is a full sphere, 2 pi r square. If it is half hemisphere, so pi r square into E. Pi r square into E. This is the second problem we did on the Gauss law. Now, next problem we discuss, if the electric flux entering and leaving an enclosed surface example problem, the electric flux entering and leaving through a the electric flux entering and leaving through a closed surface is pi 1 and pi 2. The electric flux entering and leaving through a closed surface is pi 1 and pi 2. Then electric charge inside the surface will be, then electric charge inside the surface will be question mark. Now, we have to find out electric charge inside the surface will be, the electric flux entering and leaving through a closed surface is pi 1 and pi 2. Pi 1 is the entering flux, pi 2 is the leaving flux. Then electric charge inside the surface will be, we need to find out. See here, assume this is one closed surface, this is entering flux, this is leaving flux. Entering flux we can take it as, this is entering flux pi 1, this one is leaving flux pi 2. Entering flux is pi 1, leaving flux is pi 2. Entering flux we are taking it as negative, leaving flux we can take it as positive. Leaving flux we can take it as positive. This is closed surface, this is entering flux, this is leaving flux. Entering flux is negative, leaving flux from the surface is positive. Now what we have to find out? Electric charge inside the surface is what? We need to find out. What is electric charge inside? Now apply the Gauss law. Total flux pi is equals to Q by epsilon naught, that already we know. According to Gauss law, pi total is equals to Q by epsilon naught. What is the pi total related to this one? This is negative, this is positive. So pi 2 minus pi 1 is the total flux linked with this surface, which is equals to Q by epsilon naught. Now Q we need to find out. Q is equals to pi 2 minus pi 1 by into epsilon naught. This is the electric charge inside the surface will be. Q is equals to pi 2 minus pi 1 into epsilon naught. This is the way we need to find out. Here this flux is entering, that one we are take it as negative. This flux is leaving out from the surface, we can take it as positive. Now pi total is equals to Q by epsilon naught, that is Q is equals to pi 2 minus pi 1 into epsilon naught. This is the charge inside the surface. 10 SI units. Electric flux of 10 SI units goes into a closed surface an electric flux of 10 SI units goes into a closed surface and 5 SI units come out from it, and 5 SI units come out from it. Then charge enclosed by surface is. Same case before we discussed. An electric flux 10 SI units goes into a closed surface and 5 SI units come out from it. Then charge enclosed by the surface is. This is surface. How much entering? Entering is 10 units. And how much is coming out? Coming out is 5 units. 10 units entering, 5 units is coming out. Now charge enclosed by the surface we need to find out. Entering is negative, existing is positive. Now according to the Gauss law, total flux is equals to Q by epsilon naught. Is it right? Pi total. Now pi total, this is negative, so minus 10 plus this is plus 5 is equals to q by epsilon naught. Minus 10 plus 5, which is nothing but a minus 5 is equals to q by epsilon naught, then q is equals to minus 5 epsilon naught is the charge enclosed by it. Now, up to here we discussed electric fields and charges, and we discussed some problems also in this one. This is as important for NEET concept and also EAMCET concepts. This flux and electric charge and fields, force between the two charges, electric field intensity at a point on the axial line, equatorial line, torque acting on a dipole, these are all we discussed. And that one we saw some sums also, how they are going to be asked. We discussed previous questions also on this concept, electric charges and fields. Resistance of platinum. The temperature coefficient of resistance. Resistance of platinum is 3.92 into 10 to the power of minus 3 per Kelvin at 0 degree Celsius. Find the temperature at which the increase in resistance of platinum wire is 10% of its value at 0 degree Celsius. The temperature coefficient of resistance of platinum is 3.92 into 10 power minus 3 per Kelvin at 0 degree Celsius. Find the temperature at which the increase in resistance of platinum wire is 10% of its value at 0 degree Celsius. Now, we need to find out find the temperature at which the increase in resistance of platinum wire is 10% of its value at 0 degree. We have the formula alpha is equals to R100 minus R0, otherwise RT minus R0 by R0 of T2 minus T1. Here substitute RT is what they are giving, 10% of its value at 0 degree. 0 degree is R0, so 10% of its increases, which increases the resistance of platinum wire is 10%. So, RT will become as 10% of R0 is nothing but a 1.1 of R0. So, RT is 1.1 of R0. It increases. So, the increase in resistance of platinum wire is 10% of its value at 0 degree. Then RT is equals to 1.1 of R0. Now, substitute the values. Alpha is equals to RT. RT is nothing but a 1.1 of R0 minus R0 by R0 of change in temperature delta T. T1 is nothing but a 0 degree. We need to find out T2 we need to find out. T1 is 0 degree. Now alpha value is given, what is that? 3.92 into 10 to the power of minus 3, which is equals to 1.1 R naught minus R naught. So 1.1 minus 1 into R naught by R naught of T2. R naught cancel. Then 3.92 into 10 power minus 3, which is equals 1.1 minus 1, nothing but a 0.1 by T2. So that 0.1 by 3.92 into 10 power minus 3. Then by solving this one, we will get square by 3.92. Then T2 will get value as 25.51 degree Celsius.